So today we're going to cover Chapter 1, Section 4. Today what we're going to cover is classifying polygons and finding perimeter and area of polygons in a coordinate plane. So in other words, we'll be graphing ordered pairs, connecting the ordered pairs to create a polygon, and then calculating the perimeter and the area. So for some of the side lengths of our polygons, we're going to have to use the distance formula. But let's go ahead first and define what a polygon is. So a polygon means many angles because the prefix there, poly, means many. So polygon means many angles. It's a closed plane figure formed by coplanar segments called sides. Now polygons do not have curved sides. They have to be straight line segments. Each side must intersect exactly two sides, one at each endpoint. Then no two sides with a common endpoint are collinear. And then the third, each endpoint of a side is called a vertex of the polygon. So what this means is it can't have any gaps. So when it says it's a closed plane figure, it's got to be closed. It can't be open. The smallest polygon that we can create is called a triangle. So the smallest one will be a triangle. And notice that third bullet point said each endpoint of a side is a vertex of the polygon. So if I were to label these points, I could say that this polygon has a vertex at A, B, and C. The second bullet point here, or the second characteristic, says no two sides with a common endpoint are collinear. So in other words, you can't have more than one point, more than two, like an endpoint. You can't have additional points on the side of your figure. So you can't have a bunch of points that are collinear. And then each side must intersect exactly two sides, one at each endpoint. Okay, so it wants us to identify the figures that are not polygons and explain. Well, the first one, this one is a closed plane figure. Notice there's no curved sides, and each side intersects exactly two sides, one at each endpoint. They don't have any extra collinear points. And then each one where these sides meet, these are all the vertices of this polygon. So yes, this is a polygon. It satisfied all three of those characteristics and it's closed. The next picture, notice we've got an opening right here. So this is not a closed plane figure. So this would be not. So this one's not a polygon. And the sides are not intersecting two sides. So in addition to being open, the sides are not intersecting two other sides. Then the next one, notice if we put some points here, it's intersecting. This side here is intersecting too many other sides. And again, we can't have a line here or a side with more than just two collinear points. So this one would be not a polygon. But as soon as you take away all those inside cross lines, then it is a polygon. And then the next one, E. Notice this is not a closed figure. The sides are not intersecting at both endpoints. So this one would be not a polygon. It's not a closed figure. If I gave you a shape that looks something like this, this would also not be a polygon because this side over here is curved. You can't have any curved sides when it's a polygon. Definition of a convex polygon. And what this states is that no line that contains the side of a polygon contains a point in the interior of a polygon. So what this sentence here means is this is the interior or the inside of this polygon. And then if I were to draw a line that contains the side, as long as that line stays outside, doesn't go into the interior, then this is considered a convex polygon. Now, you need to check all the sides. As soon as you find one side that would go into that green area, then it's not a convex polygon. What it'll end up being is called a concave polygon, and we're going to see that on the next slide. But notice when I trace over all of these sides, none of the red lines that I'm drawing go into the green section, which is what makes it a convex polygon. You can also think of it as all of these vertices are pointing outward. Nothing's caving in. So all of these are examples of convex. So again, here, if I were to color in and show the interior of this one, and again, if I were to trace over the sides with like a red line, the red would never enter that blue, making it convex. The next slide, you're going to see how when I draw the line, it actually goes inside, making it concave. But again, think of these vertices as just pointing outward. Next is the definition of concave polygon. This one has a line that contains a side of the polygon that contains a point in the interior of the polygon. So again, if I shade in the interior, and as soon as I trace over one of the sides, it doesn't have to be all of them, but as soon as I find a side that when I trace over it and the red line goes into that green section, then this would make this polygon concave. Another way I think of it as is this vertice that's right here, it looks like it's caving in. The side of the polygon is caving in. So when all the sides point out, it's convex. But as soon as something bends to the inside, it's considered concave. You only need to find one that caves in. It doesn't have to be all of them. Next, we're going to classify polygons based on their number of sides. So again, the smallest polygon that you can create is called a triangle. We are going to have several chapters coming up in the future that will be dedicated to triangles. So we will learn lots of different properties and information about triangles. Then the four-sided figure is called a quadrilateral. That's the general name. We will also have a chapter dedicated to quadrilaterals, and we'll learn about specific quadrilaterals like squares and rectangles and rhombuses, parallelograms. The five-sided figure is called a pentagon. 6 is a hexagon. Now notice there are two H words, but what helps me to remember that the hexagon is for the 6-sided figure. Notice the word 6 when I spell it has an X in it, and so does the word hexagon. And then the 7-sided figure is called a heptagon. 8-side is an octagon. I remember that one. I think of an octopus has 8 arms, so an octagon has 8 sides. A 9-sided figure is a nonagon. What helps me to remember that is if I spell the word 9, just like the word 9, it has 2 N's, and so does the word nonagon. Only difference is you change the vowel that's in between there. The 10-sided figure is called a decagon. I remember that as a decade, 10 years. 12-sided figure is called a dodecagon. Notice they jump over 11. I'm not going to require you to memorize any other polygon names, So if I ever ask you to refer to 11-sided figure, what you're going to use is this rule here. And when it's got 11 sides, you're just going to describe it as 11, a dash, and then GON. If I ask you to describe a 100-sided polygon, 100 sides, again, all you would do is 100 dash GON. So the only ones that I'll require you to know are what's in the chart here. Okay, so here, tell whether the figure is a polygon, and if it's a polygon, decide if it's convex or concave. Now, if it's not a polygon, we just say that it's not a polygon. We're not going to classify it. So for the first one, notice that we've got a line here splitting. So this would not be a polygon because it's two separate closed figures. So this is not a polygon. Now, if they were to have drawn it this way, this would be a polygon. This one is yes. And then what type of polygon is that figure I just drew? Concave or convex? Good, concave. Notice it looks like this vertex here, or it looks like it's caving in. Or again, you could draw the line on top of the side and notice it goes into the interior. The next one, is it a polygon? Yes, it is. Concave or convex? Convex. Now the next one, I know it's kind of hard to see, but this side has got a little bend to it. It's curved. Is that a polygon? No. No. Good. What about D? Is that a polygon? Yes, it is. Concave or convex? Beautiful. All right, so for figure A here, what we need to do is, in addition to, these are all polygons to begin with, so now what they want us to do is give the specific name and then tell if it's concave or convex. So to classify it or give its name, we need to count. So I have 1, 2, 3, 4, 5, 6 sides. What's the 6-sided polygon called?
Hexagon.
Hexagon. And is this concave or convex? Convex. Good. Notice all of those vertices look like they're pointing outward. Or again, if you were to trace over the sides, you would see that this red line does not go into the interior on any one of the sides. Now, what's also going to be coming up, but not in this lesson, we're going to learn another vocabulary term, and that vocabulary term is going to be the word regular. Whenever you see the word regular in front of any one of the polygon names, what that means is all sides are equal and all angles have the same measure. So that'll be coming up. So this would actually be a regular hexagon because all the sides have the same congruency mark, and same thing with all 6 angles. The next one, we need to count the sides as well. So notice this one has 1, 2, 3, 4 sides. What kind of polygon has 4 sides? Quadrilateral. And is this concave or convex? Convex. Okay, again, all those vertices are pointing outward. Again, if you were to draw lines, none of these red lines go into the interior. Now, more specifically, coming up when we cover the quadrilateral chapter, we're going to learn that this is actually a picture of a parallelogram. But for now, all we need to worry about is that it's a quadrilateral. And then the last figure, let's go ahead and count how many sides we got here. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. What's the 12-sided figure? Good, dodecagon. And is this concave or convex? Concave. So if you were to trace over the side, you could see that it starts to go into the interior of that shape. or think of these vertices here as caving in. All right. What we're also going to be doing in this lesson is finding perimeter and area of a figure or polygon when it's graphed in a coordinate plane. So I'm going to be giving you ordered pairs. You're going to graph them, and then you're going to need to find the length of the segments or the sides of the polygon. Now, for some of the polygons, you're going to need to use the distance formula. And that'll be whenever the sides are a diagonal segment that's graphed. If the segments or the sides of your polygon are either horizontal or vertical lines, you can go ahead and just count the little squares if you've graphed it in a nice, neat graph. If not, you could also subtract the coordinates. So you need to be familiar with the formulas for perimeter and area for triangles, squares, and rectangles. You've probably seen these formulas repeatedly throughout elementary school and middle school, and probably in your Algebra 1 course. So when you find perimeter of any shape, all you're doing is adding up all the side lengths. So for a triangle, you would find the length of each one of the 3 sides and add them. For a square, all 4 sides in a square are the same, so you could just find the length of one and then times it by 4, and then that would give you the perimeter. Or just add them all up individually. And for the rectangle, this is the formula for perimeter that you probably saw quite often, maybe even in Algebra 1 when you were learning how to solve 2-step equations. But another way that you can do this is if you recognize that this side over here is also a length and a width. So the other way to find perimeter is you could add up length plus width plus width. Again, just add up all the sides. Or another way is to take the length and the width and add it together and then double it. So the rectangle has 3 different ways you could go about finding the perimeter. Now, for triangles, the area formula is 1/2 base times height. Now, keep in mind that the height of the triangle is always going to be a perpendicular segment or a piece that is forming a right angle with the base. So for the formula of area, all we're going to do is 1/2 base times height. You might have also seen it as base times height divide by 2. Either way. And then for the square, because all sides are the same, it's just side to the 2nd power. But again, if you also want to do it as length times width or base times height, it's going to be the same thing. Just know that your length and width will be the same number, and same thing if you use base and height. More than likely, you learned length times width maybe in elementary school, and then maybe in middle school they introduced base times height. And then you can use exactly that same formula here for the rectangle. So let me go ahead and show you some examples here. Now, in our coordinate plane, when we label the units, the perimeter is always just going to be units. Unless they tell us inches or feet, it's always some kind of linear unit. And then for the area answers, it's always going to be units squared, or you might see them spell out the word square units, or abbreviate it and put SQ units. But just know area answers always have the units squared, and then perimeter is just whatever the units were. So let me give you a picture of a rectangle, and let's just try an example here. Now you're going to be graphing it in a coordinate plane, but let's say we already had the lengths. So let's say the length here is 8 inches, and the width is 3 inches. And they said, find the perimeter. So what we would do here is if we use the formula pictured up there, we would do 2 times 8 plus 2 times 3 gives me 16 plus 6. So my perimeter is going to be 22. And then in this case, they gave me a unit, so it's going to be 22 inches. Now, if it were the same picture and they said area is length times width, so all we have to do is 8 times 3, and the area answer is going to be 24 inches squared, or you can spell it out, 24 square inches. And this would be for the area. But we're actually going to be graphing them and have to find the lengths of the side by either using the distance formula or counting the squares in our coordinate plane. So example 3 wants us to find the perimeter of triangle ABC with vertice A, which is -2, 3, B, which is the coordinate 3, -3, and then C, -2, -3. Notice the little picture here in front of the letters ABC. In geometry, it's always very important to label what you're talking about. So the shortcut, instead of having to write the word triangle ABC, you can draw a little picture of a triangle, and that indicates that those 3 points, after you graph them and connect them, form a triangle. Remember, in the first section, we learned how to name a plane, and then that was important that we wrote the word plane in front of the 3 letters. So let's go ahead and graph our 3 ordered pairs. So for the first one, for A, it's -2, +3. For B, it's +3, -3. And lastly, for C, -2, -3. I'm now going to connect the points to form my triangle. So I have side BC here, side AC, and lastly, side AB. So remember, what we need to do here is find the length of all 3 sides and then add them together, and that will give us the perimeter. Remember, in section 3, when your segment that you graph is a diagonal segment, you have to use the distance formula. However, for the horizontal and the vertical sides here, we could count the little squares. So what we need to do here to find the perimeter, we need to find the length of AB, add that to the length of BC, and then also add it to AC. So for the first one, for AB, that's going to be the more challenging one because it's that diagonal segment. We need to use our distance formula. x2 minus x1 squared plus y2 minus y1 squared underneath the square root symbol. So we're going to be using the order pair A and B because we're looking for the length of segment AB. I'm going to label my order pairs. A is going to be my order pair number 1, so my x1, y1. B will be order pair number 2, x2, y2. And now let's plug them in. So I'm just going to do 3 minus -2, and that quantity is squared, plus -3 minus 3 squared, and it's under the square root symbol. I'm going to combine my terms here. This will turn into 3 plus 2, so 5 squared. This turns into -6, so -6 squared. All of these are still under square roots. Going to square the 5. Going to square the 6. I now add them You're following order of operations. I can't break this down. It is in simplest radical form. So if we're not using a calculator, we would leave the length of AB as the square root of 61. Now, once we start the Big Ideas homework, if the instructions said round to the tenths place, then we would use our calculator, square root it, and it's about 7.8. Now I need to go back and find the length of BC. So my ordered pair for B, 3, -3. C is -2, -3. So for BC, you can either choose to count the little squares. So BC is 1, 2, 3, 4, 5. BC has a length of 5. Or what you could also do is if you didn't have a graph, just subtract the coordinates. So take away the part of the ordered pair that's the same, and now subtract the x's. Remember, you absolute value it. Distance is never negative. So 3 plus 2, and I get 5 either way. So now the length of BC is now 5. And now we need to do AC. Order pair for A, -2, 3. C, -2, -3. Or count the little squares. So I could also count 1, 2, 3, 4, 5, 6. AC has a length of 6. Or get rid of the part of the ordered pair that's the same. And now do 3 minus -3. Turns into 3 plus 3. And notice it's the same answer when I subtract. So now for perimeter, remember we were using this. So we're going to add AB, which was the square root of 61. We're going to add BC, which was 5. And then AC, which is 6. Now, if it's simplest radical form, all we can add is the 5 and the 6. 61 you're going to leave there, and that would be the answer. If they had told us to use our calculator and turn the square root of 61 into rounded to the tenths place, this would have been 7.8 plus 5 plus 6, which would give me 18.8. Both of these are units. So perimeter is always just units. This picture, let's say the question instead said find the area. So my height is actually this segment here, AC, and then the base is the 5. So if the question said find the area, 1/2 base times height, all you would do is 1/2, 5 times 6. And again, 1/2, you could multiply the 5 into the 6 and get 30. And then the area would be 15 square units. The area questions are going to be a little bit easier because the height is always going to be a vertical line. So the last example, same thing. It's a triangle that we're going to form after we graph the 3 vertices. And then this time they want us to find area. Area, remember, is 1/2 base times height. Or you could also do base times height, divide by 2. So let's graph the 3 ordered pairs. I'm going to graph the ordered pair for D, which is +1, +3. And then E, +4, -3. And then F, -4, -3. I'll connect the 3 points, create my triangle. Now, if the question said find the perimeter, I would have to do the distance formula twice because I've got 2 diagonal sides there. I'd have to do the distance formula for DE and DF. But the question said to find the area. So my base is going to be the FE or the EF. So E, 4, -3, F, -4, -3. Get rid of the part of the ordered pair that's the same. 4 minus -4 gives you 4 plus 4. And FE or EF has a length of 8. You could also count the squares. So if we counted it, it's 1, 2, 3, 4, 5, 6, 7, 8. This is the base. And then the height is going to be the segment that goes perpendicular to that. So I'm going to draw in a segment that goes straight up to the highest point there of D. And this is going to be my height segment. And again, it's a straight vertical line. I could count the boxes. So if I just count the little squares, 1, 2, 3, 4, 5, 6. So the height is 6. So now I'm going to take the two numbers. I'm going to multiply base times height and then by a half. So I could take half of 8, it's 4. And then 4 times 6 is 24. And these are square units. Again, if they asked us to find perimeter, I would do the distance formula for the two sides that are diagonal. And then I would have used the 8 for that side of EF and then add them all up. Just remember, the height will never be one of those diagonal sides. It's always going to be the perpendicular segment or the segment that comes down to the base that forms a right angle.